Drone warfare is evolving faster than almost any other military technology, and at the center of this revolution are swarms and artificial intelligence. For years, drones were primarily thought of as single aircraft remotely piloted by humans, useful for reconnaissance or precision strikes. Now, the future points to a very different picture, where drones are no longer isolated tools but part of intelligent, coordinated networks capable of overwhelming defenses, adapting to threats, and making decisions in real time. The idea of drone swarms and AI-driven autonomy represents a complete shift in how militaries might project power, defend assets, and carry out complex missions across the battlefield. A drone swarm is not simply a large number of drones flying together. It is a group of drones that communicate, coordinate, and function like a single organism. Instead of one operator controlling one drone, swarms are managed through algorithms that allow the drones to work collaboratively. Each unit can share information about its environment, distribute tasks, and adapt to changing circumstances without requiring constant human input. This model draws inspiration from nature, particularly the way flocks of birds, schools of fish, or swarms of insects move seamlessly as one, responding instantly to obstacles or predators while maintaining cohesion. Translating this biological inspiration into technology requires advanced software, networking, and artificial intelligence. The performance advantages of swarms are enormous. Traditional air defense systems are designed to intercept a limited number of incoming aircraft or missiles. They may be effective against one or two drones, but a swarm of dozens or hundreds presents a completely different problem. Even if defenses intercept some of the drones, others can continue the mission. This sheer volume can overwhelm defenses, saturate sensors, and increase the likelihood that at least some drones will reach their targets. Swarms also allow for distributed risk. Losing one or two drones in a swarm is insignificant compared to losing a manned aircraft or a large single drone carrying expensive sensors or weapons. The resilience built into swarm operations means that missions can continue even in hostile environments. Artificial intelligence is the backbone that makes drone swarms possible. AI enables drones to process information quickly, detect patterns, and adjust behavior without waiting for human commands. In a swarm, AI systems help drones share data, avoid collisions, identify targets, and assign roles. For example, one drone may act as a sensor, scanning for threats, while others act as shooters, and others still function as decoys to distract defenses. This dynamic role assignment is impossible to coordinate manually, but becomes manageable when AI handles this. AI also enhances autonomy, meaning that drones can keep functioning, even if communication with their operators is jammed or disrupted. Design elements for swarm drones differ from those of traditional unmanned aerial vehicles. Many swarm drones are small, lightweight, and relatively inexpensive. Instead of building a few highly advanced and costly drones, the strategy shifts toward building large numbers of simple, modular units. Their simplicity is intentional, as it allows them to be mass-produced at lower costs. While still performing effectively as part of a coordinated group, some swarms may feature drones as small as a hand, designed to confuse sensors or carry small payloads, while others may be larger units that can deliver explosives or carry advanced sensors. The mix of drone sizes and functions within a swarm increases flexibility and makes it more difficult for an enemy to predict or counter their tactics. Performance metrics for swarm drones are not only about speed or payload, but also about networking and processing power. The ability of a swarm to communicate securely and rapidly is critical. Drones must be able to share sensor data in real time, update their positions relative to each other, and alter formations instantly if conditions change. This requires robust wireless communication systems and encryption to prevent interception or disruption. Low latency is essential, as even small delays could cause collisions or reduce effectiveness. Engineers are exploring technologies like mesh networks, where each drone can relay information to others, ensuring that even if some are destroyed, the swarm continues to function without losing overall coordination. A unique selling point of drone swarms is their adaptability. Unlike traditional aircraft that follow a fixed mission plan, swarms can adjust their strategy on the fly. If defenses are stronger in one area, they can redirect themselves to weaker points. If a primary target is destroyed earlier than expected, they can shift focus to secondary targets. This adaptability makes them more unpredictable and harder to defend against. Combined with AI, swarms can also learn from missions, analyzing data to improve performance in future operations. In military terms, this creates an iterative improvement cycle where each deployment makes the swarm more capable than before. From a strategic perspective, drone swarms open the door to entirely new tactics. They can be used to saturate defenses before a larger attack, conduct reconnaissance in areas too dangerous for manned aircraft, or act as electronic warfare platforms to jam enemy communications and sensors. Swarms can even deliver supplies in contested zones, with some drones acting as couriers while others provide overwatch or defensive functions. In naval warfare, swarms could overwhelm ship defenses by attacking from multiple angles simultaneously. On land, they could support ground troops by identifying ambushes, providing continuous surveillance, or delivering precision strikes without risking soldiers' lives. For many observers, one of the most intriguing aspects of drone swarms is their potential to level the playing field. Countries or groups that cannot afford advanced fighter jets or large navies could invest in swarms to counter more powerful adversaries. The low cost and mass production potential make them accessible. Raising concerns about proliferation and asymmetric warfare, a swarm of inexpensive drones could threaten billion-dollar assets, making them a highly attractive option for militaries looking for cost-effective solutions. This asymmetry is one of their strongest selling points, as it allows smaller powers to challenge larger ones using numbers and coordination rather than expensive platforms. Artificial intelligence also brings new dimensions to the way drones are designed and employed. AI algorithms can recognize patterns in radar signatures, analyze terrain, or even predict enemy movements. In swarms, AI can enable cooperative behaviors such as surrounding a target, dividing into subgroups to handle multiple objectives, or using deception tactics like feints and false retreats. These capabilities push swarms beyond being just a collection of drones and make them a cohesive force multiplier. The more advanced the AI, the more independent and effective the swarm becomes. Of course, this future also introduces challenges. One of the biggest is ensuring reliable control. Militaries must decide how much autonomy to give the drones and how much control to retain with human operators. Too much autonomy could lead to unpredictable outcomes, while too much reliance on human control could slow response times and negate the advantages of AI. There are also ethical concerns about AI-driven drones making decisions about lethal force. International debates are ongoing about how autonomous these systems should be allowed to become, with many calling for safeguards to prevent unintended consequences. Another challenge lies in countermeasures. As swarms become more prominent, defenses will adapt. Systems designed to detect and neutralize large numbers of small drones are already being developed, including directed energy weapons like lasers, microwave systems, and advanced electronic warfare tools. However, countering swarms remains difficult because of their resilience and adaptability. Even if defenses can eliminate dozens of drones, the swarm may still succeed by sheer persistence. This creates an ongoing race between swarm development and counter-swarm technologies. In terms of design philosophy, swarm drones are moving toward modularity and scalability. A basic drone frame might be equipped with different payloads depending on the mission, such as cameras, sensors, or explosive charges. This modularity allows forces to tailor swarms for specific roles without needing entirely different drone models. Scalability means that a swarm can be as small as a handful of drones for reconnaissance or as large as hundreds for a major offensive. The same core technology underpins both, giving commanders flexibility in deployment. The performance of swarms is also enhanced by developments in machine learning. With every mission, AI algorithms can analyze how the swarm performed, identify weaknesses, and adjust strategies for next time. This self-improving cycle mirrors how humans learn from experience, but at digital speeds, potentially creating swarms that are far more capable after just a few deployments. Over time, this could result in swarms that anticipate defenses, predict outcomes, and refine tactics automatically. Looking beyond the battlefield, drone swarms also have civilian applications, and these highlight some of their unique design elements. Swarms can be used in search and rescue missions, with dozens of drones scanning large areas quickly to find survivors. They could be deployed for environmental monitoring, mapping, or disaster response. Their ability to cover large areas, share data, and adapt to obstacles makes them incredibly versatile tools for both military and civilian use. In agriculture, Swarms of small drones are already being tested to monitor crops, distribute fertilizers, and manage pests efficiently. These non-military uses show how swarm and AI technologies could transform many aspects of society. Despite these potential benefits, the military applications of swarms are what attract the most attention, particularly because they represent a significant shift in warfare. Traditional doctrines built around tanks, ships, and aircraft must adapt to account for large numbers of intelligent, autonomous systems. Command structures must rethink how to integrate human decision-making with AI-driven operations. Logistics chains must adapt to supply, recharge, or repair hundreds of small drones instead of a few large platforms. The future battlefield will likely see humans, machines, and AI working together in complex hybrid formations, with swarms playing central roles. What makes drone swarms so compelling is not just their speed, coordination, or low cost, but the way they embody a new philosophy of warfare. Instead of concentrating power in a few expensive assets, they distribute it across many expendable units. Instead of rigid plans, they rely on adaptability and learning. Instead of centralized control, they function with decentralized autonomy. These shifts challenge traditional thinking and push militaries to reconsider how wars are fought and how victory is achieved. For the general audience, the simplest way to think of drone swarms and AI is to imagine a hive of bees. Each bee is small and individually vulnerable, but together, the hive can defend itself, find resources, and adapt to threats. Drone swarms follow a similar principle, with AI acting as the brain that keeps the hive functioning as a unit. What seems like chaos to the outside observer is in fact highly coordinated, driven by shared goals and constant communication. This combination of nature-inspired design, cutting-edge, and innovative engineering is what makes future drone warfare so different from anything seen before.